That cell tower has not moved in years, yet on its roof is an antenna listening to satellites normally associated with navigation. It is not asking where it is. It is asking a more important question: exactly what time is it? A mobile network is a vast coordination problem. Thousands of radios share spectrum, hand devices from one coverage area to another, and pass traffic into equipment owned by other networks. Those machines do not merely need clocks that run at roughly the same speed. Depending on the system, they may need agreement about frequency, phase, or the precise boundary of a time slot. If neighboring radios drift too far apart, transmissions intended for separate moments can interfere. Handoffs and network connections become harder to coordinate. Data can be lost even though every tower is still standing and every fiber is still intact. The surprising part is where that common reference often begins. GPS satellites carry atomic clocks and broadcast signals that include satellite time. A stationary receiver can use those signals to recover precise timing. The GPS control segment monitors the constellation and uploads corrections, while equipment on the ground turns the received reference into something a network can distribute. That does not mean every cell site is built the same way or that every tower has its own GPS receiver. Some systems recover satellite time at the site. Others distribute timing from a central reference through the network. Many use several technologies together, but the core problem is identical. Distant machines must share one trustworthy version of now. This is why GPS became an invisible utility. The signal arrives from space, but its real work happens inside ordinary cabinets, clock units, switches, and radios. To understand what fails when that signal disappears, we first need to separate three ideas that are often compressed into one word: synchronization. Frequency is the rate at which a clock runs. Two clocks can show different times yet tick at the same speed. Phase is the alignment of repeating cycles. Time is the label placed on a particular instant. A network may need one, two, or all three, and the tolerance depends on the technology and task. Some modern mobile requirements sit near the microsecond scale. That sounds impossibly small, but a microsecond is long enough for light to travel roughly 300 meters in empty space. At network scale, tiny timing errors become physical distances and overlapping radio events. At the receiving site, satellite time does not replace the local clock. It disciplines it. A timing receiver compares the external reference with a local oscillator, learns its behavior, and continually corrects it. The receiver may output a pulse marking each second, a frequency reference, or time data. Network clocks then distribute an engineered version of that reference to the equipment that needs it. Fiber and packet networks can carry timing too, but propagation delay, path asymmetry, calibration, and equipment error all matter. Ordinary internet time is not automatically a substitute for the tighter phase and time requirements of a radio network. Now remove the satellite signal. The local oscillator does not stop. It enters holdover. The clock continues using what it learned before the reference vanished. This is not a universal countdown. A low-cost quartz oscillator, a temperature-controlled unit, and a rubidium standard can drift at very different rates. Their recent calibration history, environment, software, and required tolerance change the result again. NISD tested one rubidium-based GPS-disciplined clock that remained within 1 microsecond for about 73 hours. That is an example of one device under one test, not a promise to every network. The important question is not, how long does GPS last after GPS is gone? It is, how long can this architecture remain inside its own timing limits? Even the cause of lost trust matters. A broken antenna or failed receiver can remove a signal. Jamming overwhelms it with interference. Spoofing presents a false signal that may appear believable. Space weather, adjacent band transmissions, or errors elsewhere in the distribution chain create different symptoms. Treating them as one problem makes detection harder. A clock that announces total signal loss can switch to holdover. A clock being fed plausible, but false time may need independent references and monitoring before it realizes anything is wrong. This is why resilient systems compare sources, watch for sudden steps or impossible drift, and know which services depend on each timing path. Multiple satellite constellations can help with availability, but they are not complete independence when receivers share antennas, frequencies, environments, or failure modes. And a network can appear healthy inside one timing island while slowly losing alignment with another network. The first failure may therefore be subtle: degraded radio performance, unreliable event ordering, or timestamps that can no longer prove which event happened first. The tower did not forget its location. The network began to disagree about now. A resilient timing system does not search for one magical replacement for GPS. It layers different strengths. Satellite timing offers broad coverage and a common reference. Better local oscillators extend holdover. Engineered packet timing and calibrated fiber can move time through a terrestrial network. Independent clocks and monitoring systems can expose a source that suddenly disagrees with the rest. The design goal is not simply to keep a clock face moving. It is to preserve traceable time within the tolerance required by each service, and to know when that promise can no longer be trusted. This is already becoming physical infrastructure. Britain's National Physical Laboratory has tested precision time distribution over fiber using technologies including PTP and White Rabbit, alongside geographically distributed clock facilities. In March 2026, the UK government announced a £180 million National Timing Centre programme intended to distribute resilient timing by radio, internet, and fibre. The point is not that satellite timing has failed. It is that systems this important should not depend on a single route. Telecommunications makes the dependency easiest to see, but it does not end at the cell tower. Power systems use synchronized measurements. Financial systems use timestamps to establish event order and audit trails. A loss of trustworthy timing does not automatically turn off the grid or crash an exchange. More often, it erodes confidence in measurements and records before it produces a dramatic visible failure. That subtlety is exactly why timing infrastructure is easy to ignore. Roads crack, cables break, clocks can drift quietly while every screen still looks normal. Strong architecture combines prevention with awareness. Operators identify which services depend on time, diversify the reference paths, detect manipulation, avoid spreading bad time, and preserve a trustworthy record of recovery. GPS remains extraordinarily useful. The lesson is not to abandon it. The lesson is to stop confusing a reliable source with an independent system. Real resilience begins when a network can answer two questions at once. What time is it, and why should I believe that answer? The hidden clock behind your phone is not one clock. It is a chain of trust. Atomic references, satellite broadcasts, receivers, local oscillators, fiber routes, network clocks, monitoring systems, and the engineers who decide when one source can no longer be believed. Most days, that chain makes distant machines agree so precisely that nobody notices it exists. The moment they stop agreeing, the physical network can remain in place while coordination begins to unravel. That is the strange power of timing infrastructure. It is invisible when it works and ambiguous when it fails. If you want to see another system hiding beneath everyday infrastructure, subscribe to Infrastructure Untold. And tell us which chain we should trace next. The clocks inside data centers, the timing behind the power grid, or another system most people only notice when it breaks.